Okay, so I'm gonna talk about CPH model, which stands for cooling plus heating model, which is a new approach to tackle the cooling flow problem in galaxy clusters. To begin with, I would like to as an introduction, in order to be familiar with a cluster of galaxies. Cluster of galaxies are a combination of hundreds to thousands of galaxies that are bound together by gravity. And there aren't just galaxies which are present in cluster of galaxies, but there is a hot plasma, a hot gas, which is emitting X-ray. And in this image, I have brought for you two images of the same galaxy, cluster of galaxies, which is Abel 2199. And in the left-hand side of this image, you can see this cluster in X-ray band. And in the right-hand side image, you can see the same cluster image in the optical band. And as you can, in this image, in the right-hand side, you can see individual galaxies. And in the left-hand side image, you can see the X-ray emitting intracluster medium gas, which is emitting X-ray. And in the middle of clusters, you can see BCG, which stands for brightest galaxy, cluster galaxy. And I will, in more detail, talk about these details in the following slides. To have a sense about the size, the mass, and the temperature, typical temperature of a cluster of galaxy, I have brought this beautiful image for you. And the typical range of the radius in clusters is of the order of megaparsec. This image is for Abel 85. The mass is between 10 power 14 to 10 to power 15 solar mass. The mass includes dark matter, hot gas, and stars. And the typical temperature in the cluster of galaxies is of the order of 7 kilo electron volts. And density, number density of electron, you can see that is 10 to power minus 3. And the magnetic field is around of the order of micro Gauss. So I showed you an image in which you could see that the intracluster medium is emitting X-ray. And because of this emission, why is intracluster medium emitting X-ray? It's mainly because of Bremsstrahlung phenomena. In that region, we have hydrogen and helium mainly, which are mostly ionized. And because of the presence of ions in that area and high temperature, when electrons are moving in the electric field of ions, they emit photons, X-ray photons, which we know it is known as Bremsstrahlung phenomena. And the power of this radiation in volume per volume is proportional to number density of electrons and number density of hydrogen atoms, and temperature, also root of temperature. So because of this radiation, cluster of galaxies are losing their energy, and we expect that they become cooler and cooler over time. And as time passes, because a great deal of energy is escaping from the clusters via X-ray radiation, we expect clusters become cooler and cooler, and as I told you. And we can define a time scale for this cooling, which we call it cooling time. And cooling time, as you can see, is defined in terms of thermodynamics, variables and quantities. And you can see that it's in terms of temperature, number density of electrons, and you can see a function here, which is a cooling function. And surprisingly enough, when we calculate the cooling time for cluster of galaxies, we notice a really interesting phenomena. We notice that in the central part of clusters, the cooling time approaches below half a gigayear. And by this time, compared to the age of a cluster, which is around 7.7 gigayear, clusters have enough time to be cooled several times. And you can see here a cooling time profile for a sample cluster. And you can see that in some radius, below some radiuses, the cooling time, this axis is for cooling time. The cooling time reaches less than a gigayear, and this leads to some discrepancies between predictions of models and our observations. Based on our calculation, we expect C clusters in this way. For example, they should be cooled down, and we should see a great deal of molecular gas and cold mass and cold gas. But surprisingly enough, what we observe is something that you can see on the right-hand side, which is a hot gas, a cluster with hot gas, still emitting X-ray photons, and we should explain this discrepancy. In order to talk about different aspects of cooling problem, the problem that I just explained, the difference between our calculations and expectations and what we observe regarding the cold mass in cluster of galaxies, I have provided the cooling profile. Here you can see cooling time. Here you can see radius for 5 specific clusters that you can see. And you can see that in some radius, less than around 10 kiloparsec, the cooling time reaches less than half a gigayear. And that problem that I just mentioned about the amount of cold mass happens here. And we cannot, as I told you, there is a difficulty in detecting any byproduct in cooling cluster from hypothesized cooling flow plasma. And another aspects of cooling problem is here. You can see that when we plot the temperature profile of cooling clusters, we notice that in some big radius, when we are in radiuses in this range, the temperature is high, and it decreases when we move toward the center of cluster. The temperature decrease more and more, but we see that in some specific radius, below some specific radius, which is from here around 10 kiloparsec to the center, the temperature tends to become quite flat, and it doesn't decrease dramatically, and it's completely against our expectation. We expect because in the central parts the X-ray is stronger than outskirts, we expect the cooling, the temperature decline more dramatically in the central parts. But what we observe is completely different. Cooling problem and the discrepancy that I just mentioned shows itself in the spectral, X-ray spectral as well. In these panels, you can see that The first panel, up panel, is the prediction of cooling flow model. And when you, in the red lines in the middle panel is observations or observation. And when we fit the cooling flow model with observation, we notice that the predictions of our model is not satisfactory. And you can see that models predict some emission lines which doesn't some emission lines which don't exist in observation. And in this part you can see that the models don't predict observations properly at all. And in order to tackle this problem, people are try to remove some parts of the cold gas from the observations. In order to fit the model, we have some integrations which have two limits of temperature, T mean and T max, T1 and T2, and this integration should be taken over 0 to T. But people try to change to define a minimum cutoff, and they don't integrate over from 0 to T, but integrate from T1 to T. And this can resolve this problem, but this is not a physical procedure. Why should we, remove some important part of plasma with temperature from 0 to T1 in order to fit our model? And in order to see, this is a problem that shows itself, and we have to take into account this important effect. And here you can see the consequences of changing temperature and its effect, that the limitation that I told you, explain just for you, the consequence and the effect of changing the integration temperatures on a spectrum. And by playing with this range of temperature, we can have and find different spectrum in order to fit observed spectrum. Okay, in order to solve the cooling problem that I just mentioned for you, we have to include a heating mechanism into clusters. And there are many different proposals suggested in order to do this. The first approach is to define a thermal energy for cluster, a thermal energy of the cluster gas. And the channeling mechanism for this would be via conduction. And hot gas from outer part can transfer heat to the central part, and they can heat the central regions. Another source for heating clusters and tackling cooling flow problem will be cluster mergers. And mergers can lead to turbulence, and turbulence can cascade, and because of the viscosity that exists in those regions, can lead to heat. Another source is galaxy motions, and galaxy motions in the clusters can produce turbulence, and turbulence can finally lead to enough heat to heat the region, central region. And finally, AGN, central AGN, can heat can be seen as a heating source, and shock and sound waves, turbulent dissipation, and mixing of gas between intercluster medium and hot content of bubbles can heat up the central region. So in order to explain our model, which is CPH, I need to explain a little bit about spectral fitting. Some important point and takeaway message is that we don't observe spectrum, we observe photon counts. And in order to make photon counts is related to a real spectrum via response function of telescope, which is the probability of observing a photon of energy E in channel I of the telescope. And the approach in order to fit some observed photons, photon counts with our model, we need to first of all define a model based on physical parameters. We can define and find a spectrum, which is Fe, and then we can use a chi-square method and compare our observations with predictions of our model. And our model will have some free parameters, and by changing those parameters, we can calculate chi-squared, and by calculating chi-squared, we can find, by doing it over and over again, we can find free parameters of our model. And in the sample that we have used in our study includes these clusters that you can see here. And an interesting aspect of these, this sample is that all members that we have chosen have cooling time less than 1 gigayear in their central regions. And we have chosen 16 annually per source, and we have used Chow software and XSpec. We have used Chow in order to extract spectra, and we have used XSpec in order to feed the extracted spectrum. And you can see that here, you can see the annually that I talked about. There are 16, and after extracting data, we can fit it with XSpec, as I explained. And in our model CPH, we use AGNs a lot. So AGNs are some compact regions in the central parts of galaxies. They include a black hole, and they have an accretion disk. They have some 2 jets. Usually they have 2 jets, and in those jets we can observe shock waves and interesting things happening. So we consider AGN. I wanna show you that if we choose AGNs as a heating source, it can provide enough heat to heat up the central part. And Zhoolideh et al. In their Nature paper 2014 they have shown that a turbulent heating rate is of the order of radiative cooling rate. And they have shown this for 2 clusters, Perseus cluster and Virgo cluster. And so we can be sure that AGNs can provide enough heat to heat up the system. So in the CPH model, cooling plus heating, in a collaboration with Professor Niaish Afshordi and Professor Khosrowshahi, we proposed a heating time scale into the system. And unlike isobaric cooling, which just includes cooling time, we have introduced a heating time which is defined in this way in our modeling. And it can lead to a different probability distribution for temperature, which you can see here completely. So in our model, we suppose that T heat is proportional to sound crossing time, and the constant of proportionality is Shakrai-Sanyaev constant, which is popular in magnetohydrodynamic and turbulence systems. And what we do is that we use the luminosity and spectrum of cooling flow model, and we modify it with our model. For this is a luminosity, this is a spectrum of isobaric cooling flow model, which can be derived from Euler continuity and Poisson equation. And then what we do is we take the emission measure of that model, and change it, modify it based on our model by definition of T cool and T heat, and we can finally what we achieve is this spectrum that you can see here. And the difference of our spectrum and cooling flow model spectrum can be summarized in this term that you can see here. Okay, so let's see what's the consequences of this modification. First of all, the emission measure of our model is completely different compared to MKC fellow model. You can see we have a peak. There is a temperature which we call it T star, which is the temperature at which most of the plasma at each annulus is located. The probability of distribution of plasma based on temperature in each annulus is related to emission measure. And you can see that they have to, MKC model have to define some cutoff for temperature, but our distribution is really natural and has a Gaussian type. So we have applied our model, you can see here, and we have two free parameters in our model, m dot and T star. T star is the temperature of the peak, and then we have fitted a spectra, and we have compared it with MECAL, one of the most popular models in spectral fitting. And you can see the results of our study. You can see there is a great similarity and consistency between our model and well-known MECAL model, both in density profile and temperature profile. And both models have quite same trend, and we have very close predictions. In order to understand our proposal more properly, I have provided this slide. If you consider this as a cluster, in each radius and annulus, you can see that there can be different parcels of gas with different temperatures, but in each part and annulus, there will be a probability distribution for temperature for these segmentations of the gas. And the peak of this distribution gives us T star. And those parts that are cooler than T star will cool down and they will move toward the center. And those that are hotter will heat up and separate from the plasma. And here you can see the delta chi-squared of our prediction and MECAL model. You can see that our prediction is much more better in many parts than MECAL model. The delta chi-squared between our model and MECAL is minus 56.9. And here I have provided observed a star formation rate against mass deposition rate, m dot, that we defined in our model. And the black points are CPH predictions, and the green points are classical cooling model. And based on these quantities, we can define an epsilon, which is cooling efficiency. And cooling efficiency for our model is 0.33, and for classic cooling is 0.01. Which shows that our model is more efficient. And the Shakurai-Sanyaev alpha that I talked about previously from our observation and fittings, we have found that it's near 0.048, which is really close to what the range of alpha should be. The range of alpha based on different studies should be between 0.1 to 0.1. And you can see that our predictions are in great agreement with other studies and researchers. We have written the codes of our model, which is publicly available in NASA website. You can search it, find it. You can find it in this address. And here you can see the parameters of our model, explanation of model, and you can use CPH model in XSpect manual and fit your future X-ray observations with our model, which has shown be really successful in fitting X-ray spectra. Finally, to conclude, I should say that typically our model provides better fit to data with respect to single temperature model, MECAL model in cluster cores. We have proposed a concrete solution to the cooling flow problem. The model predicts the cold gas mass, which is consistent with observed stellar mass of brightest cluster galaxies, and value of alpha are consistent with viscosity parameter in simulation, as well as observed turbulent energy fractions in cluster cores. And finally, we invite you to use our CPH model, which is publicly available at XSpect manual in your future X-ray spectral fitting. And thank you for your patience.